we built. It's a JavaScript app that allows us to observe, experiment with, interact with loci of triangle centers in ellipse-inscribed families of ellipse-inscribed triangles. One of my goals for this video is to pronounce the word ellipse correctly. So I want to say ellipse, 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 and not ellipse, as I so often mistakenly pronounce it. Okay, so just to give you guys a couple of pointers. Yes, so loci of triangle centers of ellipse-inscribed triangles. Okay, this is joint work. Most of the JavaScript development was co-developed with Everton Darlan, and it was done over the last 2 or 3 months. And we do have on this link here a bunch of slides that you can look at to get more details. Another thing that we have is a site where you can learn more about the principles underpinning simulation that we're about to see. So if we go to this site, for example, this Learn More site, and I have it ready here. So there it is. We actually go down one level of detail and we explain how loci are computed. We talk a little bit about how we started doing this work. In fact, we were inspired by this strophoid curve. This is called the right strophoid curve. And you can draw this purple curve here by actually affixing 2 vertices, V1 and V2, at the center and, for example, the top location on a circle, and just iterating or sliding a 3rd vertex along the circle and tracking the position of the orthocenter of this one-dimensional family of triangles. You get this beautiful strophoid curve. So this is how this whole exercise started. Very quickly we said, oh, what if V1 and V2 are affixed to points on an ellipse, for example, the right vertex and the top vertex, and you're going to be sliding P of t along the ellipse while keeping V1, V2 stationary. What are you going to get, for example, for the centroid, the barycenter x2 of this one-dimensional family? It turns out you get another ellipse, and for the case of the barycenter, you always get the same ellipse with axes that are 1/3 of the major and minor axes of the original ellipse. Okay, so what we did do, and this is the subject of this second part, is we can actually not only look at different triangle centers and their loci, we can also change the triangle family that we're going to be investigating. So today we're going to be looking at different families of triangles. If we switch back to the application, which is over here, okay, the subject of my first video was to explain a little bit what was going on when you actually look at 3 periodics, or the family of 3 periodics in the elliptic billiard, this family of dashed triangles. And we could investigate the loci of, for example, the in-center, which is the midpoint of the bisectors of each one of these vertices. Okay, the bisectors, since this is an elliptic billiard orbit, they coincide with the normal to the ellipse at every vertex. Okay, so the locus of the in-center is an ellipse as well, and we were able to switch it to the barycenter, to circumcenter by clicking here. I could vary the aspect ratio of the ellipse and figure out what was happening simultaneously to the locus of that particular triangle center of this particular triangle. Okay, now what we're going to do today, or in this particular video, is just iterate over different triangle families. This one here is the elliptic billiard family. If I go on this menu here, I can say, look, I want to also look at the homothetic family. The homothetic family is not made up of 2 confocal ellipses. It's actually made up of 2 homothetic ellipses, meaning that the internal ellipse, shown here brown, the caustic, is a scaled down copy of the outer one. However, it does not share its foci, not shown here, with the foci of the outer ellipse. Okay. Now I can also ask the question: what's the locus of the circumcenter of this family over the homothetic triangle family? So let's look at the homothetic triangle family. There it is. And similar to the elliptic billiard family, the three periodics in elliptic billiard, the locus of x3 is also an ellipse. You see that little e there indicating that this locus is an ellipse. Let's go back to the incenter. Now the incenter for this particular triangle family is not an ellipse. We actually don't know what kind of a curve this is. We could guess something like a quartic or something like that. But I know that numerically this is not an ellipse because I'm not seeing that little e sign here and I'm not seeing the little e sign there. So just so you guys remember, if I go back here to billiard, the locus of the incenter is an ellipse. If I go to homothetic pair, that locus is not an ellipse. And I could keep asking those questions. What's the locus of the barycenter, the centroid? Whoops, this one is pretty interesting. The locus of the barycenter is stationary. It's a point, and it's at the center of the Poncelet ellipse pair, the homothetic pair. And why is that? It's a well-known fact that both these ellipses here, they are known as, they're famous circumconics. The outer one is known as the Steiner circumellipse, and the Steiner circumellipse is centered on the barycenter, and the inner one is known as the Steiner inellipse, also centered on the barycenter. Another known fact about this family is that its area, the area of these triangles here, is constant. So as you go through this whole family, the area is preserved. So that's why you're seeing x2 stationary. If you go back to the billiard family, where x2 was actually describing an ellipse, okay, this family has another very fascinating property. The perimeter of this family is constant. Not its area, but the perimeter is constant. Now, I did not show you guys this in the last video, but this family also has a unique stationary point, and that's x9, the meeting point. So if I advance this guy here to x9, there's x9. The meeting point of the billiard family is stationary. How do you define or how do you construct the meeting point? You actually have to draw the so-called excenters of this triangle, and then draw lines that go from each excenter and pass through the midpoint of each side. And when you do that, those three lines, they meet at a point known as the meeting point. Well, it turns out that over the three periodics and the elliptic billiard, the meeting point is stationary at the ellipse center. Okay, very well. So let's go back to the homothetic pair. There it is. And I was mentioning to you guys that x2 was stationary. x1 is not an ellipse. x3 is an ellipse. x4 is an ellipse. x5 is an ellipse. x6, which was a quartic in the billiard pair. Let's go back to the billiard pair. This was the first number, the first triangle center in the series, which was not an ellipse, whose locus was not an ellipse. Well, it turns out that on the homothetic pair, the locus of x6 is an ellipse, and the locus of x1 is not. So in a way, they switch places, right, with respect to the billiard. All right, now let's keep going on the series because I want to show you guys a pretty interesting phenomenon. So x7 showing up as a nondescript curve, probably a quartic or something of that sort. X8 also nondescript. X9, which was a point in the elliptic billiard, here is nondescript. Let's keep going here. Here you got the speaker center, the Feuerbach point, X11, X12, and then we hit X13. Now, this point is fascinating. If you go to ETC and you look up X13, Encyclopedia of Triangle Centers, and you look for X13, okay, now let's get to X13. There you go. Now this guy is known as the Fermat point, okay? This is the point in a triangle that minimizes the sum of distances to the vertices. That's a beautiful thing about X13, and there's a series of other points connected to it. It's connected in a way to equilateral triangles. But what I wanted to point out here is that on Kimberling's series, as you go down the series from x1 to x2 to x3, this is the very first triangle center whose trilinears or barycentrics are not rational on the side lengths. All the other ones prior to that one are rational on the side lengths. This one is not. If you look at the barycentrics here, you can see that you're getting, polynomial or monomials that are rational on the ABC being the side lengths, but then you hit this area of ABC. And area of ABC, if you recall Heron's formula, is not rational on side lengths ABC. Now what happens practically, and we don't understand the mechanism exactly, but x13 and x14 and 15 and 16, the series of 4 points, they belong to a different category of triangle centers because they are non-rational on the triangle side lengths. So if you go, for example, to the elliptic billiard, okay, you're going to see that x13 is not an elliptic locus, does not generate an elliptic locus. But when you go to the homothetic pair, mysteriously, and this can be proven algebraically, although we don't understand the true nature of this, the locus of this point is a circle. And this is the first time we're actually seeing letter C here popping up, but lo and behold, the locus of x13 is a circle. Now let's look at what happens to the next point on Kimberling's list, x14, known as the second isogonic center. Okay, this is also, you can see here that the barycentrics are also non-rational or irrational on the side lengths because they contain area. Okay, and this point, I believe, is related to x13 through some transformation. This is known as the second isogonic center. x13 is known as the first isogonic center. Okay, now let's go ahead and light up x14. I'm going to use a second channel here. I'm going to put x14. Now I have to select the right, what we call mount. So we're going to select the homothetic family here, okay? Now look at what's going on. Both x13 and x14 describe beautiful concentric circles, circles that are concentric with the elliptic pair itself, the homothetic elliptic pair itself. So we thought this was a pretty cool phenomenon. Let's go to the next two irrational centers on the list. I'm going to use third channel here to display it. So I'm going to put 15 here, and I'm going to put 16 there. 16 there. And I'm going to go ahead and turn on the homothetic mount on both these channels. So I have homothetic, 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 homothetic. And look at what's happening. Now I have 4 loci, and the 4 of them are circles. I can change A over B to vary the radius of the circle. I do believe that at 3, the outer circle achieves a minimum in terms of radius. So I'm here at 3, 0, 0, 2. Let's go ahead and choose 3, right? And I can see that these 3 guys are moving along circles. Now, how cool is that? Now, let me show you guys a trick. We have this tandem bar over here, and I use this to actually lock up similar settings here across all channels. So if I lock up, for example, the mount setting, which selects the triangle family, and I just want to quickly compare these 4 loci in the homothetic pair with the 4 loci in the billiard pair, I clicked mount here, so these 4 guys now are locked up. If I go ahead and say billiard, they're going to change in tandem to billiard. So now here are the 4 loci of 13 through 15, these 4 irrational centers on the elliptic billiard. Neither one of them is an actual conic, much less a circle, right? This is what we're getting here. We're getting this really strange x15 curve, and I can change the aspect ratio of the elliptic billiard to see if anything changes. This is actually a really cool observation that once the type of curve is established, so be it a circle or an ellipse or quartic, 99.99% of the cases, if not all, if you just change the aspect ratio of the base ellipse, you're not going to change the nature of those curves. Okay, so if they're quartics, they stay quartics. If they're circles, they stay circles. If they're ellipses, they stay ellipses. So let's go ahead and change the 4 mounts in tandem back to homothetic, so we can demonstrate that. I got 4 circles now. I changed my triangle family. It's an iso area triangle family. And as I change A over B of the homothetic pair, I change the radius of these circles, but I do not change their conic nature, so to speak. Okay, so that's what I wanted to show on this video. I'll see you on the next one.